I'm going to record now. All right, so the 2 or the understood 2, it will not be written generally. It just means whatever your number is, it's being done twice, okay? 3 means we're raising that number to the third power, or we're saying b times b times b is a. The most important thing to remember about cubed roots versus square roots, besides just the number, right? That 3 means there are 3 of that base. There 3 means that needs to be divided into 3 of the same thing. The only thing you need to remember is that cube roots or odd roots can be negative, okay? Even roots cannot be negative, odd roots can be negative. The root is this number, so it's 3 for these examples, and for the previous examples on Friday, it was the number 2, okay? So if it's the number 2, you cannot have a negative, it's undefined, okay? Not a real number. But if it's a 3, you can have a real number, okay? Because just like the cubed root of 27 is 3, because 3 to the third power is 27, or 3 times 3 times 3 is 27, right? You can take a negative number, multiply by itself 3 times, and get a negative answer. The reason that the square root of -16 is imaginary and is not -4 is because you can't say -4 times -4 equals -16, right? That's just not true. That's false. But you can say that the cubed root of, what's 16 times 4? The cubed root of -64 is -4, because -4 times -4 times -4 does equal -64. I ran out of room for this one. Equals -64. -4 to the third power is -64. So if it's an odd number here, this can be odd and you'll get an odd answer. If that's an even number, I know I've said this to death, if that's an even number, you're always going to get an even answer, because a negative times a negative is a positive. If that's an even number, you're always going to get a positive answer. -8 squared is a positive number, but -8 cubed is a negative number. That's what you need to remember. If it's odd, it can be negative. If it's even, it can never be negative. So let's look at the next one. The next one is the cubed root of -125. So we know that that is 5 times 5 times 5 is 125. -5 times -5 times -5 is -125. So the cubed root of -125 is 5 because, oops, I'm sorry, it's -5 because -5 cubed is -125. -5 times -5 times -5 is 125. -125. Again, when you have a fraction, you are welcome to change it and just make this, instead of the cubed root of 8 over 125, you can say it's the cubed root of 8 over the cubed root of 125. We know that the cubed root of 8 is 2. And we know that the cubed root of 125 is +5, because 5 times 5 times 5 is 125. So the cubed root of 8 over 125 is the same as 2/5. You can throw that into your calculator to make sure. 2/5 is 0.4. The cubed root of 8 over 125 is also point. Oh my gosh, I'm so sorry. I'm not holding that low enough. So you can put that into your calculator, your answer. Make sure it gives you the same as what the initial problem was. Good way to check it. All right. we're saying that that is the number of times the answer is multiplied by itself. So because this is a negative 125, negative 5 times negative 5 times negative 5 gives us negative 125, right? Negative 8 means that we have taken negative 2 times negative 2 times negative 2 as our factor tree, right? And then 8 to the 9th means that we have taken, or sorry, x to the 9th means we have taken x 9 times. So that factor tree into prime factorization of 9 x's, right? So negative 8 becomes negative 2, we know that. And then 8 to the 9th, we need to take out pairs of 3. So these 3 x's become an x when they come out. These 3 x's become an x, and these 3 x's become an x. So negative 8 x to the 9th is negative 2 x to the 3rd power. Because x to the 3rd power times x to the 3rd power times x to the 3rd power is going to give me x to the 9th. Good. So you're just saying 9, and you can even say 9 and divided by 3 is 3. Or you can say how many groups of 3, right? Back to elementary division. How many groups of 3 are in 9? There are 3 groups of 3 with nothing left over. Really? Thank you. Oh, sorry, I'm not on my phone. 1 second. Thank you for telling me. You can't take an even root of a negative number. If n is an even positive integer, then the nth root of a to the nth is just a, but it's never going to be negative, okay? But if it's an odd integer, if n is an odd positive integer, so if this is positive, if this is odd, like 3, 1, 3, well, there's no 1, 3, 5, 7, or 9. This would be 2, 4, 6, or 8. Then your answer might be negative. But notice that if it's even, your answer is always going to be a positive number. It's inside the absolute value bar, so it's going to come out and be positive. Good. All right. Example 4. Find the 6th root of the number 64. So you need 64 to equal something multiplied by itself 6 times, right? We know that 64, if we factor tree it, can just be 8 times 8. We know that 8 can become 4 times 2, right? And then we know that 4 can become 2 times 2. So 64 is actually 6 2's multiplied together. So the 6th root of 64 is the number 2. Or you can just start finding 6th roots, right? 2 to the 6th, 3 to the 6th, and so forth. The 5th root of negative 32. Good. So if we factor tree 32, 32, it's whatever comes to your mind. It might be 2 and 16. It might be 8 and 4, right? Either one is okay. 8 becomes 4 and 2. 4 just becomes 2 and 2. 4 becomes 2 and 2. So we have 5. Ooh, okay, my phone's working. I'm going to pause. All right, negative 32 to an odd root means that it's just whatever the answer is, okay? So negative 32, because it's an odd root, the answer can be negative. So 32 is 2 5 times, right? 2 to the 5th is 32. Negative 2 to the 5th is negative 32. So here we know that negative 2 5 times itself is 32, negative 32. Here we see a -4, or sorry, a 4, which is an even, right? And we have a negative number. You can't take an even root of a negative number, so we say that this is imaginary. There is no real number. There's an imaginary answer, but there are no real answers to that problem. Okay, the fourth root of 16 is 2, right? But what this is saying is that if it's even, that has to be the absolute value, right? The fourth root of -2 to the fourth should equal the absolute value of -2, which is 2. But -2 to the fourth, -2 to the fourth is not going to be -16, it's going to be +16. Okay, that's why that is true. If this is negative and this is even, you just say no real number. Let's practice that rule. Okay, so what the rule is that n as the root and the exponent cancel each other out. And this is when n is even. And when n is odd, it's just itself. Okay, so -4 squared, it's taken to an even root. -4 squared. The root is an understood 2. If there is no number here, it's automatically a 2. The root of 2 and the exponent of 2 are the same, so they cancel. Even so, I need to include the absolute values, right? So n cancels n, 2 cancels 2, but because 2 is an even number, we're going to put the absolute value of a. The absolute value of -4 is +4. Or you can just solve it, right? You can say -4 squared is 16. The square root of 16 is 4. So if you do it by hand, we'll give you the same answer. Okay. Here is another even root. Okay. You have the same root and exponent, so they will cancel each other out. The fourth root and the fourth power will cancel each other out. The fourth root is an even root, so we need to say it's the absolute value of a, and in this case, a is x minus 2. So the absolute value of x minus 2 is, I leave it as my answer, x minus 2. Good, because of the variable. We don't know what that variable is. So we'll just leave it as the absolute value of x minus 2. You can't get any further because you don't know what x is. All right. Now, letter C is the fifth root of 2x minus 7 to the fifth. The root of 5 and the exponent of 5 undo each other, and we just get a. 2x minus 7. It's not in absolute value bars because it's an odd number. It's an odd number 5. Good. D is an understood 2. So we have 2, the square root or the second root of 25x to the fifth. This 2 undoes this 2, but only for the x, right? So we still have to take the square root of 25 is 5, and the square root of x to the second is x. So it's just 5x. So this is the same thing you're doing. It's just if it's something more complicated, you can use this rule. Okay, but we knew how to do this from how we practiced on Friday, and now we can use the rule to solve it if you want. All right. Find function values if they include radicals. Okay. All this means is just like we substitute whatever it is next to the f in for x. We're going to do that here, but then we're going to take it further if we can. Continue simplifying it if it's simplifiable as a radical. Okay. So f of x is the square root of x plus 2. F of 7 is the square root of 7 plus 2. So I just took whatever x was and I changed it to 7. The square root of x plus 2 becomes the square root of 7 plus 2, which is the square root of 9. We know that the square root of 9 is 3 because 3 squared is 9. Good. B is saying f is 0. So we're saying f of 0 is the square root of 0 plus 2, which is the square root of 2. You cannot simplify that any further. I would leave it like that. Okay. If you put it in your calculator, you get a decimal, but the decimal goes on forever. Okay. It only ends because my calculator ends it there. So it's more accurate to put it in terms of the radical. Good. So those are for f, the square root of x plus 2. Now we're going to do g with it, which is a cubed root. Okay. So g of 9 is the cubed root of 9 minus 1, not x. Good. So that becomes the cubed root of 8, which is 2, because 2 cubed is 8. Last one. G to the 10th is the cubed root of 10 minus 1, which becomes the cubed root of 9. The cubed root of 9, it's not a perfect cube, right? 2 cubed is 8, 3 cubed is 27. So it's between 2 and 3. It's not a perfect cube. 9 factors to 3 times 3, and there are no other factors. That's the prime factorization. So there's nothing we can even factor out. Okay, so we just say it's the cubed root of 9. We're done. Good. So that is the end of 7.2. And now we're going to talk about 7.3, simplifying radical expressions, which is what we did in example 6. We put 7 in for x, then we simplified, or we put 10 in for x and we simplified as much as possible. Okay. To simplify, we're going to use the product rule when we multiply, quotient rule when we divide, and that is it. That's it. Product rule and quotient rule. We've already seen them, don't worry. The product rule for radicals says if the nth root of a times the nth root of b, if the nth root of a and the nth root of b are being multiplied together, as long as the root is the same, as long as this is n for both a and b for both of those bases, keep the index, right? Keep the root and multiply what is under it. Okay, so a times b become ab. AB is called, AB in this case is just what is under the radical. Okay, n can be called the root, or it can be called the radical. These have the same root. They're the nth root. They have the same radical. The radical is n. Okay. So what we're going to do is we're going to multiply using the product rule. A to the power of 2 times b to the, or sorry, a, the second root of a times the second root of b is the second root of a times b. The second root, because it's an understood 2, right, of 3 times the second root of 5 is the second root of 15. Okay, make sure that you can't simplify it. Okay, the square root of 15, not a perfect square, right? We know some squares, so that sounds familiar. Take 15, make sure you can't pull a pair out of it, right? You can't take 2 times 2 times 3 is 15, right? 15 is 5 and 3. 5 and 3 are the prime numbers, are two prime numbers, so that is the prime factorization of 15. So you can't simplify 15 any further. The square root of 3 times the square root of 5 is the square root of 15. Good. Now we're moving on to the cubed root. It is still raised to the same index or the same root. Root index. Good. So that becomes keep n multiply a times b. 4 times 2 is 8, right? The cubed root of 8 we know is 8 becomes 4 and 2. 4 becomes 2 and 2. 2 remains 2. So the cubed root of 8 is 2 times 2 times 2. Sorry, 8 is 2 times 2 times 2. So the cubed root of 8 is 2. Good. All right. Here we are raising them both, or sorry, the index here is an understood 2. Here it was a 3. Here it's an understood 2 again. Good. So because that 2 is consistent with both of them, we can just call this the square root of and multiply it straight across. 2 over a times b over 3 is 2b, just multiply straight across, over 3a. Go. Okay, radicals don't change the rule for multiplying fractions. The rules for radicals do not change if there are variables. Okay. Oops. All right, let's go on to the quotient rule. Again, we have already seen this, don't worry. Today we are just breaking down radicals, multiplying radicals, and dividing radicals. If the nth root of a and the nth root of b are real numbers and the nth root of b is not 0, then the nth root of a over b is the same as taking them each individually, which we already did here, right? We said the third root of 8 over 125 is the third root of 8 over the third root of 125. The third root of 8 is 2. The third root of 125 is 5. So we've already done this. Don't worry. Okay. An understood 2. So that becomes the square root of 5 over the square root of 16. The square root of 5 is not a perfect square, so I'm just going to leave it as the square root of 5. The square root of 16 is 4, so I'm going to call it 4. So the simplest radical form of the square root of 5 divided by 16 is the square root of 5 divided by 4. Okay, and if 5 was a bigger number, we could check the factor tree to make sure there's nothing we can factor out, but there's nothing we can factor out. It's a prime number. Good. All right, over here, this can become the square root of 40 over the square root of 81. Good. Now we can use a factor tree because 40 is not a prime number. 40, do it any way you want. We can say 10 and 4. 10 becomes 2 and 5. 4 becomes 2 and 2, right? So what we have is the square root of 40 is the same as the square root of 5 times 2 times 2 times 2. And what we do is we take anything that is multiplied by itself twice because of this 2 comes out as itself. Okay, so the square root of 40 is, that becomes a 2 outside, and the 5 times 2 stay in. The square root of 40 is 2 square root 10. Or you're also welcome to just make that list of perfect squares. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And then take 40 and say, which one of those can I divide it by? I can divide 40 by 4, and I'll be left with 10, right? 40 is 4, and 10, the square root of 4 is 2. The square root of 10 doesn't simplify, so that's just 2 square root of 10. So you're welcome to do it that way too. Either way, the square root of 40 becomes 2 square root of 10. If we keep going, 6 squared, 7 squared, 8 squared, 9 squared is 81. So the square root of 81 is 9. So this becomes 2 square root of 10 over the number 9. Good. Okay. That is the quotient rule. We're going to use it on the cubed root of 27 over 64 and the fifth root of 7 over 32x to the fifth. Okay. Remember, nothing changes when there is a variable. The cubed root of 27 over 64 is the cubed root of 27 over the cubed root of 64. 27 becomes 3 times 9, which becomes 3 times 3 times 3, which becomes 3. So the cubed root of 27 is 3. 64 the cubed root of 64 becomes the cubed root of 8 times 8, which can become 4 times 2 times 4 times 2, which can become 6 2s, right? So the factor tree for 64, the prime factorization is just 2 times 2 times 2 times 2 times 2 times 2. Right? So these 3 become a 2 and these 3 become a 2. Because when we take them out, they become themselves. You have to take out the number that is outside, that is the index. I'm free to add it. So there are 3 2s here, so that's 2, and 3 2s here are 2. 2 times 2 is 4. Okay, so the cubed root of 27 is 3. The cubed root of 64 is 4. Again, it might be faster to just make a list of cube roots like that, or to check it in your calculator. All right, here we have the fifth root of 7, and I'm just going to write it like this, over the fifth root of 32x to the fifth. Remember when we had the third root of x to the ninth was x to the third? That is because we took that number and divided it by this one. If it was the square root of x squared, it's just going to be x, because 2 divided by 2 is 1. The fifth root of x to the 11th is going to be x squared with an x inside, because 11 divided by 5 is 2, remainder 1. Okay, so if you see that this is x to the fifth, but it's being held under the radical 5, you can just say that that is x, right? That 5 cancels that 5. And so the cubed root, or sorry, the fifth root of 32. See if we can find anything for 32. The fifth root for 32 is going to be the fifth root of 4 times 8. 4 becomes 2 times 2. 8 becomes 2 times 4. We've almost got 5. We've got 3. That 2 stays the same. That 2 stays the same. That 2 stays the same. The 4 becomes a 2 times 2. And now we've got 5 2s. So we can say it becomes 2. The fifth root of 32 is 2. So on the bottom, we just have 2x. And on the top, we leave it as 7 because 7 is a prime number. The fifth root of 7 over 2x. Good. All right. I know there's a lot today. Welcome back. Now we're just going to practice simplifying, putting it into simplest form like you do with fractions, right? If you have a fraction of 12 over 15, you can say, I can divide those both by 3, right? 12 divided by 3 and 15 divided by 3 is 4. 12 divided by 3 is 4. 15 divided by 3 is 5. So 12/15 is the same as 4/5, right? We're doing the same thing here. We're just going to make a factor tree of the square root of 40, and we're going to see what we can pull out, right? I think we've already done this one today. So what we decided was that the square root of 40 is the same as the square root of 10 times 4. 4 is the biggest perfect square we're going to pull out of 40. When we take the square root of 4, we get the 2, and the 10 stays under. So the square root of 40 is 2 square root 10. The square root of 300. And you can think about perfect squares, okay? 2 squared is 4. 3 squared is 9. 4 squared is 16. 25. 36. 42. 64. Is that 48? 7 times 7 is 49. 49, 64, 81. 100, right? And so when you get to 100, 100 is 10 squared. So if I look at 300 and I know that 10 squared is 100, I can change 300 just like I immediately went 40 is 10 times 4. 300 is 3 times 100. 100, the square root of 100 is just 10. So it's 10 square root 3. Because I took 300, divided it by a perfect square, got 10, and there was a 3 left over. When I took 300 and divided by 100, I got 3. We've already seen the square root of 15. The square root of 15, the factor tree for 15 is the only pair you can make is 5 times 3. That's not 15 times 1, right? And neither of those are a perfect square. So we're just going to call the square root of 15 the square root of 15. Cannot simplify it. Make it any simpler. Example 5, simplify each radical. Don't forget to include the 3. Okay, so we have 16, the cubed root of 16, and maybe you just know cubed roots, and that is completely fine. The cubed root of 16, we're going to go with 4 and 4 for my factor tree, but you can do whatever you'd like. Okay, you can do 2 and 8. 4 becomes 2 times 2. 4 becomes 2 times 2. So we took 16, we made it 4 times 4. Then we made it 2 times 2 times 2 times 2. Remember, if you have a number times itself this many times, you can take it out. So 2 times 2 times 2 times 2 under the index of 3 becomes 2 for those 3 2's, cubed root 2. Because it was 3 times 2 to the 4th. If you take 4 and divide it by 3, what do you get? You get 1, remainder 1. Okay, so you can also divide. 4 divided by 3 is 1 with the 1 left over. Cubed root of 16 is 2, cubed root 2, not square root 2. Cubed root of 3 over cubed root of 64. Oops. Cubed root of 3 over the cubed root of 64. Well, that we're just going to leave alone because 3 is a prime number, right? 64. The cubed root of 64 is also the cubed root of 8 times 8. 64 is 4. Definitely. 8 becomes 4 times 2 times 2 times 4. Thank you. 4 becomes 2 times 2. So There's a 3 here. So if I have groups of 3, I can take them out. Good. So that means that becomes 2 times 2, and there's nothing left over. So that's just 4. So our final answer, it's a little crowded up here, but it's the cubed root, the third root of 3 over 4, or the cubed root of 3 over 4. 2 more examples. We'll be caught up. Remember, we are not doing 7.5, okay? Example 6 also asks us to simplify the radical, but now we have variables. So again, you can say this number, the 7 divided by the 2, and see what it leaves you, okay? 7 divided by 2 is 3 remainder 1, right? Because 3 times 2, let's look at it like this. This is what we're used to. Here's the 7, here's the 2, right? How many times does 2 go into 7? It goes in 3 times. What is that number? That number is 6. Subtract that number, we have a remainder 1, right? So if you just divide 7 divided by 2 is 3 remainder 1, that means my answer is going to be x to the third, and that remainder stays under there. One of the x's stays under there because it was left over. Or perfectly reasonable things to do is write out to yourself, or say to yourself, what that x to the 7th means. That means there are 7 x's. I have a 2 right here. It's still a 2. Anytime I have a pair, I can take it out. So that can come out as an x. Okay? That can come out as an x. Sorry, I'm overlapping. And that can come out as an x. This one cannot come out because he's not in a pair. So that becomes x times x times x times the square root of x. That's the pink one. That's the purple one. That's the green one, right? X times x times x is just x to the third square root x. So we get the same answer. Whether you divide the exponent by the index, or you write it all out and take them out one step at a time, okay? The square root, understood too, of 20 over x to the 16th, the square root of 20 becomes, right? Or you can think of what you can divide it by, becomes 2 times 10. 2 remains a 2. 10 becomes 2 times 5. The 2 2's come out. So the square root of 20 becomes 2 square root of 5. The x to the 16th, we can say 16. 7 divided by 2 is 3. 16 divided by 2 is 8. We can just say that this is x to the 8. Or you can say there are 16 good. It becomes 8. Or 16 divided by 2 is 8 with no remainder. Use the quotient rule to divide and simplify if possible. Assume that all variables represent positive real numbers. Good. Okay, the square root of 20 over the square root of 5. You can change this, right, to 2 square root of 5 over the square root of 5, because we know that that is 2 square root of 5. So we knew 20 is 2 square root of 5. And we know that square root of 5 is the square root of 5. 2 is being multiplied by the square root of 5, and under here it is multiplied, the square root of 5 is being multiplied by 1, right? So we can say that those cancel, and we're left with 2. Or you can say the square root of 20 over 5, so all together, right? And say, what is 20 divided by 5? 4. Why did I decide to start writing it right here? That's enough. The square root of 20 over 5 is the same as the square root of 20 over 5 is 4. The square root of 4 is 2. Okay. Here we have 7 times the cubed root of 48y to the 4th over the cubed root of 2y. What I can say about this is it becomes 7, all of this under one radical. Okay. The cubed root of 48 y to the 4th over 2y. Okay, just like we were simplifying that 12/15 is 4/5, right? So 48 divided by 2 is 24. So that becomes the cubed root of 24. And then our rule for subtracting exponents is y to the 4th divided by y is y to the 3rd, right? Or I have 4 y's up here. I have 1 y down here. 1 is canceled. And I'm left with 3 on top. Okay, so you can subtract 4 minus 1 is 3, or you can draw a picture like that. Nothing wrong with that. So what I have is, instead of 48 divided by 2, I have 24. Instead of y to the 4th over y, I have y to the 3rd. And I need to keep that 7 in front. So this all simplifies to 7 times the cubed root of 24 y to the 3rd. But now think about what 24 y to the 3rd under a 3 means, right? That y to the 3rd and the 3 means the y can come out. So that's 7y cubed root 24. Let's look at what 24 can become, okay? 24 becomes what? 4 and 6, for example. 4 becomes 2 and 2. 6 becomes 2 and 3. So we have the cubed root of 2 times 2 times 2 times 3. That means I can pull out a 2. And the 3 is left. Okay, so 7y cubed root 24 becomes 7 times 2y cubed root 3. That 2 is multiplied with the 7. 7 times 2 is 14, so it becomes 14y. And that 3 is not with the y, the 3 is with the 3. Good. I know that was a little bit fast, but I appreciate you staying till the very end and covering so much content on our first day back from break. I will see you guys Wednesday.